Hi, you are watching a movie on variational calculus. My name is Jos Thijssen and I teach classical mechanics to second year applied physics students at the Delft University of Technology in the Netherlands. So the topic of this movie is variational calculus, where we try to minimize a functional, or we maximize it for that matter. And the functional is an object which can feed a function and the number comes out. And I try to find the function value for which the number which comes out has a minimal value. And in this case, the functions that go into the functional are subject to some other constraint, a global constraint, which means that this constraint is formulated in terms of some other functional. And this problem has a nice application, which is the shape of a hanging wire or a hanging chain. And the solution of that is called the catenary. And the catenary has nice applications, for example, in 20th century architecture. And I will touch upon that a little bit towards the end of this movie. And I hope you will enjoy it. We consider a functional j, which is defined as the integral of a function f depending on y and y primed, and it's integrated over the x, and the y is a function of x. And what we are interested in is to find a stationary value of this functional, and the stationary value is expected to include the minima and the maxima of this functional. So we search for first order variations of j being 0. Those are the stationary points, and if we find all those stationary points we have the maxima and the minima. But in addition we would like to impose a constraint, and the constraint that we impose has the form also of a functional, but that is a functional involving a function g also depending on y and y primed dx, and the k should have a predefined value. It's fixed. And that means that we consider, if we consider small deviations from the function y defined on this interval between a and b, we don't want to change k to first order in the deviation of the function y. And so the first order deviations are given here. We just calculate the integral between a and b. Then here we have the ddx df dy primed minus the df dy, well known from the Lagrange equations. We multiply that by the small deviations, and that tells us how j would deviate from its original value once we perturb the function y by a small amount, delta y, and we have a similar expression for delta k, where the function g features in the integral rather than the function f. So the variational problem we are facing is now the following. We want to have our solution subject to a constraint given by this functional k, which should have a fixed value. And that means that whenever we introduce a small perturbation delta y, which does not really change the value of delta k, so for which this variation vanishes, we also want the functional j to be constant, so also this variation should in that case vanish. And in order to simplify the notation, we introduce, for the terms in the square brackets in the two integrals, we introduce the following notation: ddx df dy primed minus df dy is curly delta f delta y. So it's a kind of generalization of the notion of a derivative. In order to make progress, we use the fact that this delta y should be small, but apart from that it can have any shape. And so I take a particular example here where the delta y has two very narrow peaks. They have surface areas a1 and a2, and we just multiply this function by the delta y, and we work out the condition that delta k equals 0. and it's not difficult to see when we use this notation for the function g that this can be written as a 1 times delta g dy evaluated at x1 plus a2 times dg evaluated at x2 delta y. So these derivatives evaluated at x1 and x2, they have the following meaning: dgx1 dy is just my derivative evaluated at the values y at x1 and y primed at x1, and the same for the second term. And we see from the condition delta k is equal to 0 that it immediately follows that dg dy taken at x1 divided by the same expression at x2 is minus a2 divided by a1. That follows directly from this equation. The condition that we are analyzing is, or the prescription that we are following is, whenever the variation of delta k is 0, and that is for this particular function consisting of two bumps that is given by this condition, then we should have delta j is 0. And so we can now calculate what that means if we take the same function and we put it into the variation of the functional j. And then we obviously obtain that delta fx1 dy divided by delta fx2 dy should also be equal to minus a2 over a1. In other words, this ratio is that ratio. So if I take, say, the function f, or delta f dy on some interval between a and b, so this is x, then there is a certain ratio between the values at these 2 points. Now let me take another function g, that's the dg dy, and that function should have the same ratio, and I can take the 2 bumps at arbitrary positions. So I can vary x1, I can vary x2, I can vary a1, I can vary a2. And so the only way I can always satisfy these 2 equations is when the function g, dg dy, follows the same shape as that of df dy. In other words, what we find is that the dg dy is proportional to df dy. This is reminiscent of the Lagrange parameter in ordinary function minimization, finding stationary values of ordinary functions depending on many variables. It's completely analogous, and also the Lagrange function that plays an important role can be generalized here. So what we are doing now is we look at not at the functional j, but we look at the functional j minus lambda k, and that should be stationary. And then, of course, we do not yet know here what lambda is, but we find solutions in that case for the functions y. So from this we get functions y depending on this Lagrange parameter lambda, and they should satisfy the constraint. So this has a fixed value, and that fixes the value of lambda. Now this procedure that we have just derived for finding the stationary functions of a functional which where the solutions are subject to a particular constraint has a beautiful application in the so-called catenary, which is the problem of a chain which is suspended to 2 points on the ceiling, and what we ask ourselves is, what is the shape of that chain? Would it be like this, or would it be like that, or something else? So there is a constraint, and the constraint is that the chain is not extensible, so its length is constant. And so we make a start by representing the shape of the chain by a function y of x, which is the distance at horizontal distance x, from the axis connecting, from the horizontal line connecting the two suspension points. So we have a function y of x, and we would like to express the length of the chain in terms of the function y. Well, we know how to do that, because we can, again, just like in the Breches de Groen problem, chop up the chain into small segments, and we find that the L is a sum of all these lengths, which are called ds, and by Pythagoras' theorem we find that this is given by square root of dx squared plus dy squared, and then we can write this in the convenient form 1 plus y prime squared dx, and dx runs from, in this case, minus L over 2 to plus L over 2. We choose that for the boundaries, and they appear here in the integral. So this is fixed, and therefore this defines my constraint. So what is the functional that we need to minimize? Well, that is the potential energy. The chain will try to minimize its potential energy, and therefore we try to find an expression for that. And that potential energy can also be given in terms of such an integral. The mass of the chain is its mass per unit length. Let me call that rho, because lambda would be a little bit confusing now. So rho is mass per length. So we multiply that by the length of a small chain segment, and then the potential energy is that mass times g times y. And then if we proceed with the ds similar to here, we find that this is g times the y times the square root of 1 plus y primed squared dx. So this is my functional k, which depends on y, the function y, and this is my functional j, which also depends on y. And it also, the integral runs also here from minus L over 2 to plus L over 2. So the final Lagrangian that we have to find the stationary solutions for is j minus lambda k. In this case I've dropped the g because we can absorb the g in this parameter lambda, and an overall prefactor doesn't change the shape of the solution, and therefore we have y minus lambda, that's this lambda, times, in both cases, the square root of 1 plus y prime squared dx. And we know how to tackle such a problem. We just calculate the Hamiltonian form of this integrand. So if we call the integrand h, which is little h, which is a function of y and y primed, then we need to calculate y prime times dh dy primed minus h, and it's easily done. So here we have a y primed, it's this y primed. Then we take the partial derivative of h with respect to y primed. The y minus lambda is then just a constant, and the derivative of this with respect to y primed is given here. It's y prime divided by the square root, and then we just copy h here, and that should be constant. And so we can write that a bit more neatly by extracting a y minus lambda in front of the expression here. Then we have a y primed squared divided by the square root, and we write the second square root as 1 plus y primed squared divided by the square root, so that the square roots are now the same, and then we see that these two guys cancel, and we see that the final expression is minus y minus lambda divided by the square root of 1 plus y primed squared is a constant. The solution to this differential equation, because after all it's a differential equation, it's an equation for y primed, is given by this form: y is a cosine h alpha times x minus x0 plus b. I will not show how you get to that solution, but you can easily verify it by substitution. And then the derivative of the cosine h is a sine h. 1 plus sine h squared is a cosine h squared, and that cancels then against the cosine at the top. Now there are several constants occurring in this equation. The first one being the x0, so the x0, that should be 0 by symmetry. So we see that the chain, it should hang of course symmetrically, and the center here is x0, so the function should be even, and that can only be the case when x0 vanishes. Secondly, the value of alpha, it should be chosen such that this indeed leads to a sine h squared without a prefactor, and so this y already carries an a. The derivative gives you an extra alpha, so alpha times a should be plus or minus 1, and therefore we find that alpha is 1 over a. Plugging then the solution again back into the equation, we find two more conditions: a is equal to c and b is equal to minus lambda. And lambda should obviously be related to the length, because the length of the chain has not yet occurred in the solution. Then we have obviously the boundary condition that at the ends of the chain the y should be 0. If I apply that, we have lambda is equal to minus c cosine h L over 2c, and lambda is the same as b. And if we evaluate for that solution the length of the chain, we see that that length is connected to the value of c, and then via the value of c to the value of lambda. So this fixes all the constants that are present in this solution. The catenary has nice applications. If you look outside and you see power lines, you know that the shape of the power lines are cosine, hyperbolic cosines. They are just catenaries. It also has its application in art. The Catalan architect Gaudí, famous from the Sagrada Familia, the Cathedral of Barcelona, has built a very beautiful mansion in the years 1906 to 1910. And if you go to the top floor of that building, you will find a lot of corridors which are bent, and they all have ceilings where you find arches with a hyperbolic cosine shape. They are all catenaries, and there is also this disc with all kinds of chains suspended to it, where you can admire the beautiful shape of hyperbolic cosines. You also find these hyperbolic cosines in the Sagrada Familia itself. He loved really using that for the form of an arch. Another interesting example is the Arch of the West in St. Louis. This is commonly known as the gateway arch, and it has the form of hyperbolic cosine. In fact, it is a catenary which is put upside down, just like the arches of Gaudi. And a very nice property of that shape is that if you build an arch of this form, then the force which the top of the arch exerts on the bottom at any point is directed along the tangent to the arch. So you never have a pressure outward or inward. So in that sense, it's the most stable form that you can think of.